graphs often hide their real structure inside communities. Louvain finds those clusters with NetworkX, so the network becomes easier to explain. This is the setup you'll be able to run after this, which clusters connected nodes into Louvain communities. I'm Professor Pi, teaching AI foundations with simple Python. Louvain is a fast heuristic for finding communities in networks. In practice, it helps when you have many connected items and you want to discover groups that interact more inside than outside. People use it in social analysis, biology, recommendation systems, and fraud detection because it is scalable and often finds useful structure without heavy tuning. Success looks like clear groups that match known categories or that give new hypotheses to test. Louvain greedily merges nodes to boost modularity. Modularity being the score that rewards edges inside groups and penalizes edges across groups. Imagine two tight friend triangles with no links between them. Louvain should return those as separate communities. It's fast and simple, but remember, it's a heuristic. Small bridging edges can change the result. We will build a small example to watch that happen. First, the clean triangles, then a single bridge, and finally a weighted tweak to recover the original clusters. The goal is to learn by watching how modularity moves and how a small change can restore clearer communities. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. This next snippet builds the minimal graph and runs Louvain to show the baseline communities. This snippet builds a simple NetworkX graph and extracts Louvain communities. The edges variable lists two separate triangles, so G contains two dense groups with no cross-links, which is exactly the hidden structure we want to recover. Calling the NetworkX Louvain communities function with a fixed seed keeps the heuristic deterministic, returning a list of sets where each set is a community. Cluster members sorts those sets into readable lists, so it's easy to eyeball the result and reproduce the experiment. The print shows two clusters with their members, confirming Louvain finds the two triangles. Those clusters look good, but we need a number to say how good. The next snippet computes quality scores and a simple graph density so we can compare structural measures. This example uses NetworkX quality metrics to quantify the Louvain partition we just built. The modularity call evaluates how much the communities keep edges inside versus outside, giving a numeric sense of how meaningful the partition is. NetworkX density computes the global edge density, 2 times m over n times n minus 1, which is a coarse backdrop for the community-focused modularity score. The print reports both modularity and density, so you can see that even with modest density, the Louvain grouping can still score highly. Now imagine adding a single edge that links the two triangles. The next snippet adds that bridge so we can watch how modularity and the partition change. This code adds a single bridge edge so students can see how Louvain reacts when previously separate groups become connected. G.edge introduces the cross-link between A3 and B1, changing the topology, but leaving the dense triangles intact. Running NetworkX Louvain communities again recomputes the partition, and quality.modularity recalculates the score, so mod new captures the new community quality. Mod drop subtracts the new score from the earlier modularity to quantify how much the bridge hurt the partition. The print shows the modularity drop and the new number of clusters, illustrating that even one connector can weaken community definition. Small connectors are common in real networks. One easy strategy is to treat edges as weighted and downweight suspicious bridges. The next snippet gives every edge a weight and then weakens the bridge, so Louvain can prefer the original triangles. This snippet adjusts edge weights so the Louvain run can discount the bridge without throwing away the rest of the structure. The loop sets every edge weight to 1.0, creating explicit attributes that the algorithm will use when optimizing modularity. Lowering the A3B1 edge to 0.2 weakens that bridge, and sorting the partition keeps the output deterministic for inspection. Calling quality.modularity with the weight parameter recomputes modularity under this weighted view, letting us see whether the tweak restored community quality. The print reports the improved weighted modularity and the lighter bridge weight, showing how a small weight change can recover clearer clusters. Finally, we summarize the weighted communities into simple per-cluster statistics, so the result is easy to interpret and report. This code summarizes the weighted Louvain result into interpretable statistics for each cluster. COM-map turns the partition into a node cluster index for quick lookups. The loop computes a weighted degree sum per community using g-degree with the weight argument, then stores an average strength in AVG strengths. Rounding keeps the printed numbers friendly, while still showing the relative magnitudes between communities. The print surfaces per cluster average strength and the label for A1, confirming the tuned partition, now shows balanced connectivity. In a real project, you would map these toy labels to user cohorts or protein families, and use the average strength as a proxy for within-cluster cohesion. The same pattern scales detect the clusters, measure their quality, perturb the graph, and then retest what changed. Louvain is a fast way to find dense groups in networks, good for exploratory clustering when exhaustive search is too slow. It works well on big graphs, but remember it's heuristic and can be sensitive to bridges or weak links, so always check modularity and consider edge weights if results look unstable. Next step, try tuning edge weights or add a simple weight function based on interaction frequency to see how stability and modularity change at scale. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.